Welcome to our video on counting our way to probabilities. The objective for this video is basically just calculating permutations and combinations, i.e. learning how to count systematically so that we can solve various probability questions. So it's important to know how many events are in a sample space. If you don't know that, then you can't figure out the total. It's also important to know how to count up the good, because remember, probability is just good over total. So in this section, we're going to introduce some counting methods that will help you guys figure out how to get those good and totals, right? How to count both of those things. A tree diagram is a great way of kind of organizing your thoughts and making sure that you're counting all of the possible choices of outcomes without missing any and without counting any more than once. A simple example would be flipping a coin 3 times, right? So you're going to start, and your first flip is either heads or tails, right? And then your second flip for both of these is again heads or tails, heads or tails. And then the third flip, same thing, right? Heads, tails, heads, tails, heads, tails, and finally heads, tails. And so now the end of each branch represents an outcome. This top branch is getting all 3 heads, right? And then this branch is heads, heads, tails. Then this one, of course, is heads, tails, heads, and then heads, tails, tails, and so on and so forth, right? So a tree diagram is a great way to help you organize your outcomes, make sure that you don't count any of them twice, and make sure that you don't miss any. There are also other ways of being systematic about just listing H's and T's that will help speed up this process so you don't have to draw a tree diagram each time. Okay, the fundamental counting principle just simply says that if you have a sequence of n experiments where the first experiment has k to the 1 outcomes, the second experiment has k to the 2 outcomes, the third has k to 3, and so forth, the total number of possible outcomes for the sequence of experiments is their product. It's a big fancy way of saying if you have 5 choices, 4 choices, 7 choices, 10 choices for each stage, then the total number of outcomes is just going to be all those numbers put together. So a simple example to help kind of make sense of this is, let's say you have 6 shirts, 5 pairs of pants, and 3 pairs of shoes, and of course all of them go together. The question is, how many different outfits can you create? Well, 6 times 5 times 3, and you just have 90 different outfits. Okay? And if we did a tree diagram, you would have 6 branches, and then on the end of each of those 5, and on the end of each of those 3, and that would list all of the various, where each branch would have maybe a different colored shirt or whatever it happens to be. But it's a lot easier to just multiply together. Okay, to tackle more complex questions, you have to ask yourself, am I putting things back or not? So they'll talk about picking things with replacement or picking things without replacement. And it's the idea of, pick cards out of a deck, or take colored marbles out of a bag or something like that. It's all based on, well, when you take one out, do you put it back before you take the next one? Because it makes a huge difference whether you pick with replacement or pick without replacement. So just make sure you're paying attention to the details of the question when you're trying to calculate these things. So let's see if we can put this into practice. So in order to log into your new email account, you have to create a password. The requirements are it needs to be 8 characters long, consisting of 5 lowercase letters followed by 3 numbers. If you are allowed to use a character more than once, i.e. with replacement, how many different possible passwords are there? Well, this is where I like to introduce my dash technique. The dash technique is just a way for you to kind of formalize your thoughts and get everything organized better. If you have to have a password of 8 characters, you need 8 dashes. It's very simple. You always have the same number of dashes as the number of choices you have to make, right? If you're going to pick 4 cards out of a deck, 4 dashes. If you're going to roll a die 2 times, 2 dashes. If you're going to make an outfit consist of 3 things, pants, shirt, and shoes, and you got 3 dashes. So in this case, an 8 symbol password has 8 dashes. Now it has to have 5 lowercase letters followed by 3 numbers, and we can repeat things. So how many possibilities do we have for the first character if it has to be a lowercase letter? Well, there are 26 letters in the alphabet. And because we can repeat, we could have A type of thing, then we're going to have 26 in all 5 of the first dashes. And then it has to be followed by 3 numbers, which again, we can repeat. So if we can do the digits from 0 to 9, we have 10 choices, 10 choices, 10 choices, and that's going to be a really big number. Now I want to point out how repeating and not repeating changes things, because if we can't repeat letters, then we don't have 26 choices for the second letter. How many do we have? That's right, 25, because whatever this first letter was, this second one can't be it. And then how many choices do we have for the next one? 24, because it can't be either of those two. And then 23 and 22. Then we pick our first number. We've got 10 choices, but then we only have 9 and then 8. And you can see that that's a different number, right? Those two numbers are vastly different. So picking with replacement and without replacement makes a big difference. So you have to pay attention to the details. All right, so in case you're wondering, that's the big number that represents when you can replace it. If we were going to do it without replacement, like I said, things change, right? Our choices go down each time, and now that's the number of replacements, which is a huge difference, right? That's, what is that, 5.6 billion? 11.8 billion. Or is that million? 1,000, 100,000. Nope, that's million. That's billion, right? So more than doubled, going from 5.6 to 11.8. Okay, a factorial, n apostrophe, which is not an excited n, it's just n factorial. So when you see that little exclamation point, did I say apostrophe? When you see an exclamation point, that means factorial. And a factorial just means take whatever that number is and multiply it by every single positive integer less than that number. So 4 factorial equals 4 times 3 times 2 times 1. And so obviously 5 factorial just equals 5 times 4 times 3 times 2 times 1. And we can do this all day long. 0 factorial is defined to be 1. So that's important. We need to define 0 factorial as 1, otherwise the math falls apart. So that's just kind of the odd thing. You just need to know that 0 factorial equals 1. Okay, so here's some simple examples. 8 factorial, we can see it's just all those put together. 3 factorial over 0 factorial, well, that's just going to be 3 factorial over 1, right? The next one is where factorials are really cool, because 89 factorial over 87 factorial would be a ginormous number over another ginormous number, and it would be impossible to calculate either one of those things in the calculator. It would just be too big to display. But if you look at the pattern, this is 89, 88, 87, blah, 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 all the way down to 1. This is going to be 87 all the way down to 1. These are all going to cancel out, right? Everything's going to cancel, and all you're going to be left with is the 89 and the 88, which is a very small, reasonable number. So factorials cancel, they reduce very nicely, which makes the math awesome when we have to do some of these things. Because 7 factorial over 5 minus 1 factorial becomes 7 over 4, right? And the 4, 3, 2, 1s cancel on both, and you just get 7 times 6 times 5. Okay, our last example, 5 factorial over 3 factorial, and then 4 minus 2 factorial. Well, of course, 4 minus 2 becomes 2. The 5 factorial is 5, 4, 3, 2, 1, and the 3, 2, 1 and the 3, 2, 1 cancel. And then you're left with 5 and 4 and 2 and 1. 20 over 2 reduces down to 10. This last example is actually an example of a combination. A combination is where we're choosing a certain number of things from a group of objects, and order does not matter. So how many ways can you pick 5 books from a collection of 20 books to take with you on vacation? Do you see that it doesn't matter in what order you choose 5 books if you're just taking them all as one big group of books with you on vacation? So that would be a combination because order does not matter. If, however, you were going to choose 5 of your books to display on a shelf, then order would matter because you're displaying them in an order. So the same 5 books rearranged is a new display on the shelf, right? So when order matters, it's a permutation. Okay, let's see if you can decide which one is a permutation or a combination. In how many ways can first, second, and third place prizes be handed out to science fair winners if there are 30 students participating? Does order matter or not? Good. Yes, order matters. And what I tell my students, if you have any trouble with that, visualize running the experiment once, right? So you got 30 students, pick 3 of them, just randomly pick 3 kids to get first, second, and third, right? And we'll just label them Bill, Jane, and Steve. Well, first, second, third. But if you take those same 3 kids and rearrange them, Jane, Steve, and Bill, now it's a different outcome because you have different people getting first, second, and third, right? So order matters, it's a permutation. If each department needs 2 student representatives from each major on a campus committee, how many ways can the biology department choose representatives from the 45 students who are majoring in biology? Can you see that that's a combination? Because we're now just choosing 2 student representatives and throwing them on a committee. So if you choose Bob and then you choose Jane, isn't that the same thing as first choosing Jane and then choosing Bob? The same 2 people are going to be on the committee. It doesn't matter in what order you chose them. So therefore, it's a combination. So if you can make a choice, take those things and rearrange them, and it doesn't change the outcome, it's a combination, right? We made a choice, these 3 people. Rearrange their order, and now it's a new outcome because we have different prizes being awarded. If 3 people just all got a $5 gift certificate, it wouldn't matter, right? You could rearrange them, and they all still got a $5 gift certificate, and that would be a combination. Okay, here is the formula for a combination. Might look kind of confusing, but remember those are just factorials. And we read it as n choose r. So n is the size of the pool of objects you're choosing from, and then r is how many of those objects you are choosing. The previous example said we had 45 students and we had to pick 2 of them, right? So that would be a 45 choose 2. And a 45 choose 2 is simply 45 factorial, right? Because that's my n, over 2 factorial. And then this is 45 minus 2, which is 43 factorial. The 43 is going to cancel all those other numbers out, and we're just going to have 45 times 44, and on the bottom 2 times 1. And that's going to reduce down nicely. Combinations and permutations will always, always, always give you a whole number. If you don't get a whole number, you messed up. You made a mistake somewhere. They will always reduce down to just a simple whole number. Okay, you'll never get a fraction, you'll never get a decimal, always be a whole number. The permutation is almost the same thing. Again, it's n pick r, right? For a permutation, instead of choose, we say pick just so they match the P and the C, but it doesn't matter. I mean, you still got n number of things and you're going to collect a certain number of them from them, and you've got n factorial over n minus r. If we go back here, you'll see n factorial over n minus r, and the only difference is that r factorial. Now, my dash technique works with these, both of these as well. We're picking 2 kids to put on this committee, so we need 2 dashes. How many choices do I have for the first kid? 45. How many choices do I have for the second kid? 44, because you can't choose the same kid twice. Because order doesn't matter, we number at the bottom of our dashes and we get the exact same thing. For permutations, order matters, right? We've got, I think it was 30 kids that were getting first, second, and third place at the science fair. So we've got 3 dashes because we're giving out 3 prizes. We have 30 choices for the first, then 29, then 28. And because order matters, we leave it alone. We don't do anything else. And that is our answer. If we plugged it into the formula, right, if we did 30 pick 3, which is the 3 kids getting the first, second, and third, you've got 30 factorial, and then on the bottom, 30 minus 3 is 27 factorial, and you can see you get the exact same thing because you get 30 times 29 times 28, and then the 27s cancel, right? 27, 26, all the way down to 1, those all cancel. So the dash technique is a great way of calculating combinations and permutations as well. It just helps you count. All right, let's try another example. Let's calculate the number of possibilities for our sandwich example. Suppose there are 18 toppings to choose from once you've decided on bread, meat, and cheese. How many different possible sandwiches are there if you choose 4 different toppings? All right, well, how many dashes do we need? That's right, we need 4 because we're choosing 4 toppings. Now, it doesn't say anything about repeating, but does it make sense to choose the same topping twice? You know, I'm going to take lettuce, tomato, lettuce again, and then onion, right? That doesn't make sense. So we're going to assume we can't choose the same topping twice. It would kind of make sense to choose meat twice if you want to double the meat, but it doesn't make sense to have like double the tomatoes. They're still going to let you choose 3 more, right? So we're going to say we've got 18 choices for the first topping. Since we can't repeat it, isn't it just going to be 17, 16, and 15? Are we done? Is this how many different toppings we can have? Well, ask yourself, does it matter in which order you choose your toppings? If you say, hey, put lettuce, tomato, onion, and pickle on my sandwich, is that different than saying put lettuce, pickle, tomato, and onion on my sandwich? No, same 4 toppings. So order doesn't matter. And when order doesn't matter, it's a combination. And when it's a combination, we do 1, 2, 3, 4. And that's going to be the number of ways we can do toppings. Now, if we wanted to do it with the formula, it's an 18 choose 4 because it's a combination, and combinations are when order doesn't matter. And of course, the 14 factorials cancel out. And look what you're left with. Right here is exactly what we had on the previous page. Here's my 4 dashes. 18, 17, 16, 15. On the bottom, I had 1, 2, 3, 4. Isn't 4, 3, 2, 1 the same thing as 1, 2, 3, 4 when you multiply, right? When you multiply, order doesn't matter. That's the commutative property. So there are 3,060 different combinations. All right, how about an example using permutations? Now, make sure that when you're going through these examples, you're asking yourself about, okay, why is it a permutation? Why is it a combination? Because even though I'm telling you off the top, right at the beginning that, hey, this is a permutation, when you're doing homework or a quiz or a test, it's not going to be that easy. It's just going to give you a question and say, how many ways can you do it? And you have to recognize whether or not it's a permutation. So consider a race with 140 participants. How many possible outcomes are there for the top 3 positions of gold, silver, and bronze? If you weren't sure that this was a permutation, you ask yourself, all right, let's pick 3 people, A, B, and C. Now, if I take those 3 people and rearrange them, B, C, and A, is that a different outcome? Well, yes, it is, because they're getting gold, silver, and bronze. And if you rearrange them, they get different metals. So order matters. It's a permutation. Here's the permutation. But we could also do it with the dash technique, because if we're giving out 3 metals, we need 3 dashes, and we have 140 choices, then 139, and then 138. And because order doesn't matter, we just multiply those together and don't do anything on the bottom, and we get exactly what's down here. And there's our big number of ways that can happen. All right, another example. How many possible ways are there to arrange the order of appearance for the contestants in the local talent show if there are 15 contestants altogether? It's a really poorly worded sentence. What they're trying to say is, how many ways can you schedule the performers to come out, right? You got 15 contestants, and how many ways can you order them to come out and perform? So, does order matter? Well, yeah, doy. I mean, it says order right there in it. And also it says using permutations up top. But again, if it didn't, how do you recognize it? You know that if you rearrange them, it's different. It's got the word order in it. We know it's a 15 choose 15, which becomes 15 factorial over 0. 0 factorial, remember, we had to define it as 1, otherwise these types of questions wouldn't work, and we get this big, huge number of the number of ways we could do it. But we could also use the dash technique, because if we're choosing 15 people, we have 15 dashes, and we fill in those 15 dashes with 15, 14, 13, all the way down to 1, and we would have got the exact same answer. Most calculators can do permutations and combinations if they're the fancier scientific calculators or graphing calculators. One such calculator, the Texas Instruments ones, if you own one, great. If you don't, there are free emulators out there. This is the Wabbit EMU. I'll pull it down so you can see it. Wabbit EMU. You can go online, you can download it. It works on Windows and Mac machines. They also have an Android version, so you can use it on your phone and tablets. You have to find a ROM file for it, and those can be a little tricky to find, but they're not too difficult. Once you load it with the ROM file, it works just like the normal calculator. If you're going to do any of these permutations, combinations, types of things, they're all under the math, and then you have to scroll over to PRB for probability. You'll see NPR right there, so there's your permutation. NCR, there's your combination, and then there's a factorial if you're just going to do a factorial. So if we wanted to do this one, 15 choose 15, you have to put in the first number, the n. Then you go to math, over to probability, down to NPR, right? Because we're doing a proportion. We're doing a permutation. Put in 15 for the second one, hit enter, and there's the big old number, right? It's just listed as a scientific notation. Okay? So you don't have to do these things by hand. There is technology for all of it, so don't panic. Okay, the last kind of counting technique we have are when we have to deal with permutations with repeated objects. You'll notice that in all of these questions, whether we were doing permutations or combinations, the number one thing was we couldn't choose the same thing twice. That was really important. But when you can choose the same thing twice, so there's repeated objects and they look the same, then you have to divide out by all the ways you can rearrange those like objects that you can't tell the difference. So this is a very ugly, complicated looking formula if you were just to look at it, but let me explain it to you. N factorial is what it always is. It's the number of total things you're choosing from, so that's easy. All these little k sub 1, k sub 2, k sub 3 things, all those are is the number of objects that are the same. So K1 just represents the first object that has other objects that look like it, and then K represents how many of them are the same. And then K2 is the second object that has, let's say, twins, and how many of them there are, and so on and so forth. So you're just dividing out by all of those factorials. Let me give you a simple example, and you'll see how it works, and it's pretty simple, pretty easy. Okay, how many different ways can you rearrange the letters in Mississippi? Well, how many total letters do we have? We have 11 total letters, so that's N. But if you took this S and swapped places with them, wouldn't it still be the exact same Mississippi? And in fact, if you took that S and swapped them, wouldn't it be the same? And if you swap the two P's, it'd be the same. If you swap the P and the I, obviously that would be different, right? Okay, so to use the formula, it's very easy. You start off with how many things you have, which are 11. So that's going to be our n factorial on top. And then the bottom numbers, the 1, the 4, the 4, and the 2 factorial, those just come from repeats, right? There's one m, so there's my 1 factorial. There are 4 i's, 4 s's, and 2 p's. Now, obviously, you don't have to do 1 factorial because 1 factorial is stupid. It's just 1. But it's just there to point out that you technically do have a factorial for every different object. And then the number just represents how many of those objects we have. So we had 1n, 4 i's, 4 s's, 2 p's. So there's my 11 factorial. I'm going to stop and cut off the two 4 factorials and then just be left with 4 factorial and 2 factorial because 1 factorial is just 1, right? So we're not going to bother with that. So now we just have 11 down through 5, and then on the bottom we have 4, 3, 2, 1, and then 2, 1, right? Because the 4 and the 2. Obviously you can get rid of the two 1s and then be left with 4, 3, 2, and 2. Now you could start canceling these things if you wanted. The 4 and the 2 will kill off the 8. The 3 and the other 2 will kill off the 6 and just multiply by what's left, or just slap it in your calculator and multiply these, divide by those, and you'll see that there's 34,650 ways to do Mississippi. Okay, so those are all the different ways we can count. It's basically permutations, combinations, and repeated objects. All of them can be done with the dash technique, except for the repeated objects one. That one's a little trickier with the dash technique. And then all of them can be done in technology.